Thanks for your time today. My name is Ed. I'm a co-founder and chief scientist at Offchain Labs, the developers of Arbitrum. And I like to talk about ideas. I like to talk about practical ideas. So I'm going to talk about some of the thinking that we've been doing in our research community about how to optimize the speed of rollups. And I'm going to go in a slightly different direction than you might expect. Because I like to talk about ideas, I'm not here to tell you that Arbitrum is the leading, technically and by share, L2 stack, or that you should definitely use the Arbitrum chain or the Arbitrum orbit stack, although it is and you should. But enough about that. Let me talk about how to make rollups go faster. Okay, let me start though by talking about design, because it's important when thinking about how to make something faster to first understand how it works, sort of what are the parts. So let me spend just a couple minutes walking through the design and the logic of the design of Arbitrum as a state-of-the-art rollup. So the design consists of 4 separate components which are designed to operate together, but which operate asynchronously from each other. And that aspect of the design is quite important, that these are asynchronous and that they are designed to operate separately, each with a special job. So you have sequencing, execution, data management, and proving. The job of sequencing is to do one and only one thing. It's to put transactions in order. That is to record the transactions that have arrived, put them into some canonical order, and then publish that order. That's all the sequencer does. The sequencer is not involved in proving. It's not involved in anything else. Just put transactions in order. Once we have an ordered list of transactions, then there are 2 things that can happen next. The first one is execution. So we have a set of transactions. Execution takes those transactions, puts them into blocks, and executes them. So computing the blocks from that sequence of transaction is the job of execution. And the beauty of this is once you have a canonical list of transactions, execution is fully deterministic. And that means everyone can do it locally themselves if they want to. And then you know what the canonical state of the chain is. So execution can happen in a perfectly concurrent way. You can do it yourself if you want. You can do it on your ordinary laptop. The other place that those sequence transactions go is to data management. And this is a part of the design of these systems that is often overlooked, but actually is really critical and poses some unique challenges that are unique to L2s. What data management does is it takes that sequence of transactions that have been emitted by the sequencer, and it causes them to be archived onto either L1 Ethereum or some other data availability layer. And there's a lot of work that goes on here in this layer to do that efficiently, to batch and to compress, and to think about the timing of data posting so as to have the lowest amortized cost per transaction, because that cost is going to be passed on to users. And one of the big advantages that Arbitrum has had over time is doing this in a really careful and sophisticated way. And then the final part is proving, which is a separate component from the rest. And what proving does is it convinces the L1, everyone else already knows the result because they know the canonical sequence. It's been emitted by the sequencer and now posted onto L1 and become final there. But proving proves to the L1, the only party in the world that doesn't know the result, what the canonical result is, and it allows the canonical result to be checkpointed to the L1. And so what proving does is it shows that if you execute the transactions that were recorded to L1 by the data management layer, using the deterministic execution rule of the execution layer, that you'll get a result, a particular result, or actually a cryptographic commitment to that result. All right, so that's the design. There are a couple of decentralization, but how can we make this faster? Before we talk about how to make it faster, I want to review a couple of important decentralization principles which constrain what we can do in making it faster. First, that every user should be able to run an execution node if they want to, on the equipment they have. And that means that ultimately the throughput of the chain, one of the limits on the throughput of the chain, will be how much can be done on a sort of nominal user laptop in terms of execution. Second, the other decentralization principle that's important, at least for us, is that every user should be able to force the chain to make safe progress. With the equipment that they have, again, without needing to buy some kind of high-end equipment or some giant stack of things, a user should be able to force safe progress if they see safe progress not happening. So we don't expect every user to be working hard at this every day, but we do know that there are many thousands of nodes that are watching the chain and many thousands of people that are ready to step in and force safe progress if they don't see it happening. Okay, now, ultimately, given those principles, one of the fundamental limits to how much throughput we can get on a chain is this fact about any user being able to run an execution node. We need to make sure that the execution of the chain doesn't use more resources than that user node can provide. And so what are the scarce resources that we might need to worry about? What are the resources that might be overrun on an end user computer if we're not careful? Well, there's a lot of them. It could be compute cycles. It could be call data, the amount of data that that forms the input transactions. It could be the size of the chain's history. If nodes have to have all the history, a certain amount of the history, we might worry about that. It could be the size of the state. That is just the sheer storage required to store the state of the chain in order to execute it. It could be the bandwidth to a disk or database to read and write the state in order to do execution. It could be something like the amount of state that needs to live in RAM at any given time in order to make the amount of progress we want. It could be something like network bandwidth. And I could go on, but the point is there are many resources. And if any of those resources is used by chain execution beyond the capacity of a nominal user node, then we have a problem. And so if we just turn up the gas limit, eventually one or more of these resources are going to run out. So the problem we have is how can we stay within those constraints while going faster? Okay, so we know that L2s have more throughput than L1. L2s currently provide and L3s currently provide about 97% of the capacity of the Ethereum stack. L1 is now about 3%. So L2s have been quite successful at scaling Ethereum. But one of the facts about performance and throughput is people always want more. There's more pressure on resource use really than ever before as we see the growth of app chains and as costs come down. Now, if we want to do more, there are really two things we can do. One is within the node software itself, we can use resources more efficiently. The other thing we can do is we can price or limit those resources more precisely so that we're not limiting performance in times when we don't fundamentally need to. And of those, the first one is a matter of detail engineering, and the second one is really a matter of thinking about the economics of chain resources. I'm going to spend most of my time on the economics because, frankly, I think that's kind of a more interesting and less explored area. And as I said, I like to talk about ideas. I think there's more new and interesting ideas there. Okay. So what do we know about performance and improving performance? Performance, throughput of software is a bottleneck phenomenon. Every resource has a limit. Every resource imposes some upper bound on performance. That is, if you just crank up the gas limit, every resource will eventually hit its limit, and you better not turn up the gas limit past there. And the tightest bound, as we turn up, if we just turn up the gas limit, eventually some resource will hit its bound, and then we're at the limit. That is the bottleneck resource. Now, if we somehow magically fix the use of that resource so that we use it more efficiently, we can then improve performance a bit more, but we're going to hit another resource bound soon. And one of the inconvenient truths about performance optimization is there is no one amazing trick. You find the bottleneck, you fix it, you can increase performance on a good day 30% by doing that. Now you have another bottleneck. You attack that and repeat forever, right? The way you get orders of magnitude improvement in performance is by piling up a lot of those 30% wins, where you knock down the next bottleneck, and then you discover what's the bottleneck after that. So if somebody tells you, just do this one thing and you get 100x performance improvement, you should be super skeptical, right? This is all about thinking about bottlenecks and how to manage them. Okay. So let's talk about resource accounting and pricing. How can we make sure that we are actually using resources up to the limit of what that nominal user node can provide? In order to do that, we want to track in consensus state, because pricing is part of the semantics, the logic of the chain, any resource that could become the bottleneck. Ideally, we'd use some kind of multidimensional pricing, and there's been a lot of talk about multidimensional pricing, but there are some practical barriers there. There's some really interesting ideas coming from online optimization theory. And in fact, you can really do an interesting deep dive kind of on the theory of how to do this kind of stuff, because there is a lot of work on how to optimize performance in complex economic spaces. I don't have a lot of time to go into that. But let me talk fundamentally about what it is that chains are doing in order to manage resources. In the blockchain space, because we don't identify our users and we don't have the power to reach into their bank accounts and extract money, fundamentally all resource management is done by limitation and by pricing. We use economics to manage and limit resources. So fundamentally, if you're designing a chain, you're in the business of managing resources by pricing. You are selling resources to the transactions that run on your chain. So in terms of how best to sell those resources, we can learn a lot from the experience of L1 chains like Ethereum. Ethereum has, as I'll talk about in a minute, a good design, but not one I think that goes as far as we need to go. But if you're designing a rollup, you have another problem, because you are also, unlike L1, a buyer of resources. You are buying data availability, either from L1 or from someone else. And there's not much experience in the blockchain space with having a blockchain that buys resources from someone else. When you buy a resource, you don't get to decide how much of that resource is available, and you don't get to decide what price you're going to pay for it, right? What price you pay is results from a market interaction with your supplier. So thinking about how blockchains can buy resources is a really interesting new area. Okay, but let's talk about selling resources. Our goals here are pretty simple. We want to make sure we don't overrun the resource limits. We want to make sure that we retain a simple and compatible user experience. That is, we don't want to blow up the user experience that users A, are accustomed to, B, are comfortable with, and C, is actually supported by the wallets they're going to use, whether we like it or not. All right. And then finally, we want to make sure, though, that transactions can use a resource if that resource is available. Today's method that's used on L1 and on other places is good for the first two of these constraints, but not really great for the last one. Why is that? Well, the way we set the gas limit is we say, for each resource, what is the worst case workload? What is the workload that stresses that resource the most? We figure out how much gas that workload would use, and then we make sure that the gas limit is lower than that. That means what we do, so this gives us an upper bound on the gas limit. Actual gas limit is the lowest of these upper bounds. That's sort of logically the conversation that goes on in setting the gas limit. So what we're doing is we're limiting gas based on the worst possible case, whether that worst case is happening or not. So a simple idea sort of opens up a new way of thinking about this, and that is, let's not throttle usage or raise price based on this hypothetical worst case. Let's think about resource limitation and pricing based on what is actually happening on the chain right now. That is, if we're worried about history growth and we set the gas limit low because we're worried about potential history growth, but history is not actually growing, then we don't need to squeeze the gas limit or raise the price because of history growth concerns. So let's price based on what's happening, not on some hypothetical that we worried about in advance. Now, if that hypothetical happens, we do need to squeeze and raise the price. But until it does, we can be better. So this requires that we track actual use of resources, or strictly speaking, some conservative proxy for them, and also that we throttle when and only when some constraint on resource use is actually approached. So it's a fundamentally, and this is something that we're working. We have an active research project at Offchain Labs to understand how to do this and how to build it. And I'd be happy to talk offline about that. Now, time is short. I want to take a little bit of time to talk about the economics of data management. This is the place where rollups are buying resources. So for most resources, we set the limits and prices. But here we don't. We are a buyer in this market. And because the operation of the chain and the economics have to be in consensus, they're part of the semantics of the chain, we need a mechanism that can act as a buyer in this very complex market. Okay, the market for data blobs is actually super complicated. The dynamics of it are complicated, and we had this big stress. Now, I want to talk about just one thing here because my time is short. And that is something that happened a couple weeks ago. Something happened which I've never heard of a precedent for this anywhere else in the world of economics, although maybe some economist will correct me. That one morning in June, the price of data blobs on Ethereum went up by 13 orders of magnitude. And automatic programmatic mechanisms on all of these chains had to deal with that 13 order of magnitude increase in the price of an input. This gives you an idea of how challenging this market is. There's a lot of interesting work going on there. Again, time is short. I'm happy to talk to anyone offline here. But I hope I've provided some ideas and sparked some thinking about the issues of resource pricing, both as a seller and a buyer. And I hope I have motivated the idea that we can do much better, that we can price based on actual occurrence rather than on worst-case hypotheticals. There's a lot of space to grow the performance, the throughput of L2s while still allowing users to be first-class citizens. And I look forward to working with the community to build this out over time. Thank you very much.